avalanche, an avalanche.
Avalanche, deadliest avalanche in modern California history.
Avalanches are becoming more and more deadly. With 9 people being killed in a single 2026 Tahoe avalanche, we need a solution. Today, traditional avalanche forecasting systems use regional weather models, field observations, and scientific judgment. However, most of these systems require humans to go out and record data, which poses a risk to human safety and also makes it unreliable for hazardous places like the Himalayas. Furthermore, models often have an unspecific 500-kilometer radius prediction zone and is often unavailable for remote areas without weather stations. By using satellite data, we can remotely predict avalanches anywhere on Earth. After collecting data from publicly available sources, I was able to get over 7,000 data points on avalanche positive and negative conditions. I then filled in missing values from the dataset using the k-nearest neighbors algorithm. The data was then standardized using Smoot and Shapley's value-based feature analysis, which evened out avalanche positive data and lowered its standard deviation. This also taught us that the change in water level after 3 days is the most contributing factor to avalanches, with temperature differences coming in second. Next, I trained several baseline machine learning models on the process data, with neural networks achieving the best results. However, many of its outputs were unrealistic and contradicted physical laws. To solve this, I used physics-informed neural networks to teach the model conservation of energy in the form of a partial differential equation. The equation states that the change in temperature over the change in time has to equal to a scaling factor that's multiplied by the change in energy in the form of radiation and heat flux. This taught the model the first law of thermodynamics and limited unrealistic predictions. The equation was then passed into the model's loss function, which penalized itself for outputs not satisfying the conservation of energy. Another improvement I made was to prioritize false negatives over false positives to reduce the chance of missing a real avalanche. And I did this by prioritizing a high recall and F-beta score while training the model. These changes allowed the model to get an accuracy of 97.4% and a recall of 95.9%. I then used this model to develop a website that allows users to select the location and gather data and statistics about avalanche risk in a 2 to 5 kilometer radius. The website also comes with a 7-day forecast, personal suggestions, and alternative routes which you can take. In conclusion, we were able to successfully predict avalanches using machine learning and introduce a new physics loss function. Future improvements could involve using in-source satellite data to detect wind drifts and terrain deformations. We could also visit the idea of analyzing avalanches using computer vision and extract the data to feed into our current machine learning model.